So I know you all received the email about this, but let me reiterate it, that you should all come to the Fong Symposium. So I was happy to see some of you yesterday. We have Richard Stanley visiting us from MIT. And today he's going to give a very nice talk. Actually, this is wrong. 4:10 p.m. on Science 210. And actually, so you should come to the talk today, and you'll see that it's actually related to some of the things that we've been doing in class. Particularly the permutation side of things. So he's talking about permutations, and he's going to discuss some things that we have discussed in this class, and I think you'll enjoy the talk. So you should come. And there's refreshments before that, and then there's also a reception afterwards and a dinner afterwards, so feel free to join us for any of these things. Okay. So I was in the middle of proving this theorem last time for you, that the weak order is a meet similares which I said complete here on Wednesday, but after talking to Jim Smith about this, so I know that there's several meanings for the word complete, and so I would rather avoid it. And let me just tell you what I mean by complete. So I mean that any subset has a meet. Where any such that any subset has a meet. Where a meet means a greatest lower bound. So when I say something is a meet similares, I mean that this is true for two elements. Every two elements have a meet. And I proved that last time. But now I would like to show that not only do any two elements have a meet, but any arbitrary set of elements has a meet. Okay. And so let me prove the other half. Now, if you've taken a class where you have learned about Noetherian rings or about Artinian rings, then this proof is going to look very familiar to you. So I'm going to take any subset of my Coxeter group, and I want to find a meet for it. Prove that it exists. Okay. And so basically, I mean, the plan is very simple. The plan is that you can imagine that here is the poset. Now, let me draw it like this, because I keep drawing posets like this, but I don't want you to be misled, because remember that these posets can be infinite. They very often are if the Coxeter groups are infinite. Okay? So I have my finite set here, A. No, it's not finite necessarily. A is just any subset. Okay? And I want to prove that I have a meet. And the thing I'm going to do is basically just start taking meets of these guys. This one, meet, this one, meet, this one. And I'll show that eventually I'll get to my meet. Okay? So first let's take one of these guys. Okay? Let's say that it's this one right here. And then I say, is this guy lower than all the other ones? Well, you see, if it is lower than all of the other ones, then I'm finished, because that would mean that this is the meet. Why is this the meet? Because of two things. First of all, it is lower than anything in A. And second of all, if you had a lower bound for A, that lower bound would have to be less than or equal to x1. So that would prove that this is the meet. So if so, x1 would be the meet of A. Okay. If not, then I'm going to find something that is not greater than it. Okay. So I take maybe this to be y1. Let's say that it's not less, and then what I do is that I take the meet of these two guys. Okay. So I take x2 to be the meet of x1 and y1. Okay. So here it is, the meet of x1 and y1. And now I ask myself, is that a lower bound for everything? So is x2 less than or equal to all of A? Now, again, I claim that if it is, then it's the meet. Why is that? For two reasons. First, it is less than or equal to all of A, so it's a lower bound. And second of all, if you had a lower bound for all of A, that lower bound would have to be less than or equal to x1, which is in A, and less than or equal to y1, which is in A. And that means it would have to be less than or equal to their meet, which is x2. And so that proves that x2 is actually the meet. So if x2 is the meet, I mean, if x2 is less than or equal to all of A, I'm done. And if not, I continue. I find y2 in A, which is not. Which doesn't have this property. And then I just take the meet of that guy with x2, and I call it x3. And then I repeat this argument. Is x3 less than or equal to all of A? If it is, then I can show in the same way that x3 is the meet. And if not, I continue. So I continue. Now, what I would like to justify is that this process has to end. Why does it have to end? Because maybe I should have done the next step here. Here I had x2. Now I found a y2 which is not less than it, which is not greater than it. Let's say it's this one. And then I took their meet. And here's x3. Okay. Now I want you to notice something. That because x2 is the meet of x1 and something, x2 has to be less than or equal to x1. Right? Because it's the meet of x1 and something. But x2 cannot be x1, because if x2 was x1, that would mean that x1 is less than y1. And by definition, x1 is not less than y1. So that means that x2 is strictly less than x1. Okay? And if I repeat the same exact argument, I'm going to see that x3 is less than x2, and so on. And so when I do this process, I start with x1, I find the smaller x2, I find the smaller x3. And so what I have is a descending chain, x1, x2, x3, etc. So I have found these guys satisfy x1 is bigger than x2, it's bigger than x3, etc. Okay. But we know that this cannot go on to infinity, precisely because we started at a certain level of the poset, and we're going lower and lower and lower in the poset. This poset is a graded poset, and so really you are becoming lower, and so the largest number of steps that you could have here is the length of x1. You can't have any more steps. So that means that this process must end. So this process must end at some xk, and that xk is the meet. So again, if you've seen this, this is exactly like the descending chain condition for ideals. And the proof is exactly the same. And so basically, now you can see that this property you can think of as a sort of a finiteness property for meet semilattices. So the only reason that a meet semilattice might not have this property is if it has infinitely long chains going down. And that tells you what sort of meet semilattice could not have this property. Okay. Any questions about this theorem? So let's prove a corollary of this. It's a very nice corollary. This is that if W is finite, then the weak order is actually a lattice. And saying that it's a lattice means that every two elements have a meet and they have a join. Okay. I have a meet which is called X meet Y, and I have a join which is called X join Y. Okay. Why is this? Proof. Let's take X and Y in the poset. Okay. So let me draw the poset. Now, here's what I want to say. I want to say X and Y have at least one. I mean, I want to show that they have a least upper bound, right? That's what it means to have a join. To have a least upper bound, first I better check that at least I have one upper bound. Okay. So do X and Y have an upper bound? Is that obvious? I want you to think about whether this is really obvious or not. But we have a candidate, right? It's the top element. But is it obvious that this top element is greater than everything in the poset? By the way, I realize now that you let me make the mistake that I asked you not to let me make, which is that I should always put R's under my inequalities, right? Because here we're talking about the weak order this whole time. You shouldn't let me make this mistake because I'm not going to let you make it. So it's good practice. And that's the key here, right? The key is that we know this inequality is true in the Breuard order, but is it true in the weak order? Is that obvious? I mean, remember, we know the opposite way, that if you have an inequality in the weak order, that's an inequality in the Breuard order, but that doesn't go the other way. So it could be that this inequality holds in the Breuard order, but not in the weak order. Okay. Well, I'll show that it does. So trust me for a second, and the next thing I'll do is show you why this is true. But so this means that at least I have one upper bound. Okay. And so now let's consider the set of upper bounds. So let A be the set of elements of the poset which are bigger than X and bigger than Y. Okay. So this looks something like this. These are the things that are bigger than X and bigger than Y. Now, I'm supposed to show that there's a least upper bound. This is the set of upper bounds. So what I should be doing is showing that there's a least element here. What do you think this one is? It's basically the meat of all of these guys. So let's consider, let's call it W to be the meat of A. Okay. So why is this the least upper bound? Well, basically because it's less than or equal to any upper bound, and it is an upper bound basically by definition. Okay? So then you just check easily that W is exactly the meat of X and Y. It is an upper bound, and it is the smallest such upper bound. And I keep making the mistake. Right. Okay. Any questions about that? This is, by the way, this is a very useful tool if you want to prove that something is a lattice. And very often when you want to prove that something is a lattice, you would want to prove that there's a meet and that there's a join. And very often in practice when you want to do this, you will find that one of them is very easy to prove and the other one is not so easy to prove. So, for example, those of you who took the matrix class saw that happen exactly. The meet in matrix is very easy, the join is not so easy. But how do you prove that something is a lattice? Well, one way of proving it is just by proving that it's a semi-lattice, like a meet semi-lattice, and it has a top element. And if you prove that, you just repeat this argument and you have that it's a lattice. Or if the join is easier, then you prove that it's a join semi-lattice and that it has a bottom element. And once you prove that, you will have that it's a lattice. So this is a good proof to keep in mind, not just in this class, but whenever you're dealing with lattices. Okay. Okay. How do I prove this? How do I prove that the top element really is the top element? I mean, so far I just know that it's the highest element in the poset. But how do I know that it's really greater than everything in the poset? How do I know that it's the highest element in the poset, first of all? Okay, because remember that we showed that the weak order is graded, just like the Bruhat order. Yeah? So the floors are the same in the weak order and the Bruhat order. Okay? But let's actually prove that this is the biggest guy. Okay? And the way that I'm going to prove that is by showing you something that we showed for the Bruhat order, and I will show that it's also true for the weak order. That if you consider the map that multiplies by the longest element, then this map just flips the poset, reversing the order. Okay. Order reversing. Okay. So remember what this means is you have the poset. Now if you multiply everything on the right by W naught, what that does is exactly that, it flips the poset. Why does that prove this? Because we do know that the identity is smaller than anything. The identity is less than or equal to everything in the poset. And so now multiply the poset by W naught, that flips, and that proves that since the identity was smaller than everything, when you flip, now it becomes the top element, which is now bigger than everything. Okay. So this will imply this. Now, it's also true that if you multiply on the left, you get an order reversing map. And if you decide to multiply by W naught on the left and the right, then it's going to be a consequence of these two things, that when you multiply on the left, you flip the poset. When you multiply on the right, you flip it again, and you get it back to what it looked like. So order preserving. So these are three statements. And like I said, these two imply this one. So let me prove the first one. Now, the thing is, remember that I proved that the weak order can be characterized in this way. It can be characterized by the relation of containment, that the reflections that shorten U are a subset of the reflections that shorten B. Okay. So when is U W naught less than or equal to V W naught? Well, it's basically when the reflections that shorten U W naught are contained among the reflections that shorten V W naught, by definition. Okay. But if you go back to your notes, you will find that we proved that the reflections that shorten W naught are exactly the ones that don't shorten U. So this set is exactly the set of reflections that don't shorten U. And this set is exactly the reflections that don't shorten V. This we proved, so you just look it up in the notes. You'll see that we proved this when we were talking about these reflections. And then we're done, right? Because basically, the complement of this is contained in the complement of this if and only if this guy is contained in, contains this guy. And this is equivalent to saying that U is greater than or equal to V. Okay. So that proves this statement. That proves this statement, which proves this statement also, that W naught is the biggest element in the weak order. Now, I'll leave it as an exercise for you to prove this one. It's actually easier. And then once you have this one, then as a consequence, you're going to have the third one. Okay. So for the second one, it's going to be an exercise. Yeah?
Over here, we're in the middle of the left-hand board. It says take x1 equal a. You can't do that unless a is not empty. So you needed e non-empty there. But if a were empty, then its greatest lower bound by this theorem over here would be the top element. You're okay. So if you had proved this thing first, then the empty case would work in there as you stated.
I see. Yeah.
That's why I got confused.
Yeah. I meant to say non-empty.
Yeah.
But if you have a top element, then it's considered that its meat is the top element of the poset.
Everything is an upper bound
Yeah.
of the empty set, so the greatest or the least upper bound of the empty set would be, well, whatever. So
Yeah, exactly. As long as there is a top element, which is the condition over there. Okay. Okay. Let me say a couple of words about why this is nice. So we have a Coxeter group, right? And so a Coxeter group has this multiplicative structure, which is the structure of a group. Now, what we're doing here is that we're giving the Coxeter group an additional structure of a semilattice. And if you think about it, a semilattice can also be thought of as a kind of a multiplicative structure, where you think that the multiplication, quote unquote, is the multiplication of A and B is A meet B. Okay? Now, there are equivalent ways of thinking about meet semilattices, so we can think about them in this way, but you can also think about them as completely algebraic structures. Okay? Let me just, well, I'll just say this. So you can also think of a meet semilattice as a set with an operation that has three properties. That the operation is idempotent, meaning x meet x is x. That's clear. It's commutative, x meet y equals y meet x. And it's associative, x meet y meet z is x meet y meet z. Okay? It's clear that meet semilattices have these three properties. And these three properties are enough to characterize meet semilattices. So if you have any set with an operation that is commutative, associative, idempotent, then you can prove that there's a meet semilattice behind there. Okay? And so really, now you can think of having a Coxeter group that has the group structure and this other structure, which is also, you can also think of as an algebraic structure of a multiplication of the meet. Okay? And this gives you an additional tool to study these Coxeter groups. Now, there's an interesting question, which is, if you know the group structure, can you tell the meet structure? Well, we just saw how we do it. But now the opposite question, if I only tell you the meet structure, can you tell me what group I'm talking about? Yeah. And that's an interesting question that you can read about in the book. But the answer is that in most interesting cases, if I tell you the meet semilattice, then you can tell me what group it is. Okay? And so that's pretty interesting. And that's something that you might actually read about for the project and study exactly how this works. But this gives you kind of a nice alternative point of view to think about Coxeter groups. So this is one of the nice things about this result. There was another nice thing I wanted to say about this weak order, which is the following. I told you this. Whenever a combinatorialist discovers a new poset that seems nice, one of the first things they're going to want to do is compute its Mobius function and see if it's nice. So for example, we saw for the Bruhat order that it was very nice. It consisted of ones and negative ones. And you proved that in your homework. Well, you in the homework together with me in class proved that. Okay? I'll post a solution on the website for that too. Let's compute the Mobius function for this weak order. So this is the weak order of S3. So what's the Mobius function? Well, what you do is, again, you start with a 1 in the bottom. Let's compute just the Mobius function mu of bottom element comma something. Okay? So mu of bottom element comma bottom element is 1. And then remember, at each step, you just take the negative of the things underneath. So underneath this, we have only this one, so negative 1 and negative 1. Here, underneath this one, we have negative 1 and 1. So we get a 0. And the same thing here, we get a 0. And this maybe gets you worried and makes you think, okay, this is not going to be as nice as the Bruhat order. Here, you get 1. Okay? The zeros might worry you. Now, it turns out that this Mobius function is very nice. And it's not always 1 and negative 1, but it is always either 1, negative 1, or 0. So this is a theorem that the Mobius function of the weak order of u comma v is either 0, 1, or negative 1. And I can tell you exactly when it's each one. So it's minus 1 to the something when v is equal to u times w naught of j. Oh, you can't see this anymore. If V equals U W naught of J. So let's remind ourselves what this means. W is my Coxeter group, S is my generators, J is a subset of S, and W0 of J means that you take the subgroup, the parabolic subgroup generated by J, and you see if that parabolic subgroup has a maximum element. And if it does, that maximum element is called W0 of J. So if V is obtained from U by one of these maximal elements of a parabolic subgroup, then you get -1 or 1. Otherwise, you get 0. That's the theorem. To prove this, actually the only proof that I know of this fact is topological. Remember that I told you that the Mobius numbers of a poset can be thought of as Euler characteristics. And 0, 1, and -1 are nice Euler characteristics. And so one way of proving this theorem is just by understanding topologically what these things represent. And I mean, of course, this requires some background, and so I won't show you that. But it would be nice to find a combinatorial proof. And my feeling is that it shouldn't be so difficult. I mean, just like for the Bruchard order you did it, I think here you should be able to do it also. And I just have never seen it, but I imagine someone has done this before. And again, this would be a nice thing to work out if you would be interested in it. Okay.
So what is the importance of this Mobius function? I mean, can we use it to maybe measure how far away from each other posets are? I mean, what is the significance of it?
So John's question is, what is the significance of the Mobius function? Now, that's a very large question in and of itself, but one answer is that the Mobius function generalizes a lot of things that you know and care about already. For example, if you've ever used the inclusion-exclusion formula for counting, you really are using the Mobius function. You just haven't noticed yet. Or in number theory, one of the most, a very useful tool is called the Mobius inversion formula. I don't know if you've seen this before, but it's something that they use all the time, and it is also using this very directly. It's a story that would take me, I mean, there's a lot to say about this question. There's a lot to say about these Mobius functions, but maybe a short answer is that it is very useful as a tool to compute combinatorial quantities that have to do with your poset. So for example, when you want to compute quantities that are related to the weak order, then it's very likely that you will end up using this. Okay? When you're counting sets, then a lot of the things that you do when counting sets have to do with the Boolean poset, and that's why you end up using inclusion-exclusion a lot. And so whenever you're counting something and there's an underlying poset, it's very likely that you are using the Mobius function, or it will be a very valuable tool. That's the short answer. Okay. And again, a long answer could be a project. So if someone is interested in studying the uses of the Mobius function in Coxeter group theory, that's a very good project. Okay. Now, I told you at the beginning of this class something, which is that Coxeter group theory can really be thought of as a place where there's a big interplay of algebra, combinatorics, and geometry. And so far, you might have the feeling that I'm ripping you off as far as the geometry is concerned, because we've done a lot of algebra, a lot of combinatorics, and not so much geometry. And my next goal in this class is to salvage that and actually start doing some geometry and start thinking of Coxeter groups in a geometric way. And so the starting point for that is to tell you this story about the weak order from a geometric point of view. And I think that it's, at least in my mind, it's the way that I prefer to think about it, about the weak order. Okay. So let me show you how to think about the weak order in a different way. Let's do it for a concrete Coxeter group that we like very much, which is the group S3. And let's do it in this example that we like very much of the system of mirrors. Okay. So we're looking at these mirrors right here. Okay. And so what the group that I have underlined here is the group generated by the reflections across these lines. Okay. Now, we said that if let's say that this is the room that we're actually in, and these are mirrors, and then these are all the reflections that appear when we look at ourselves in the mirror with these two walls. Okay. So this is home. And now let's consider these two reflections by these two mirrors that are surrounding us. Okay? S1 and S2. So we talked about this. And we said that basically you can think of this as you reflected by S1. This is S2. Now, how do I get here? I get here by reflecting S2 across S1. So first I do S2 and then I do S1. I get here by first doing S1 and then S2. And then I get here by either doing S2, S1, S2, or equivalently S1, S2, S1. So this is our nice geometric way of thinking about the symmetric group S3. Okay. Now I want you to look at the Brughat order. I want you to look at this picture, and I want you to realize that they're basically the same picture. What do I mean concretely by this? I mean, put a vertex in each one of these regions and draw a line whenever you have a mirror separating those two regions. Yeah, so what I get is exactly this picture. I have a vertex inside each region. I put an edge if there's a separating mirror, and so what I get is exactly the picture of the weak order. And this is not a coincidence. This is true in general. If you want to think about the weak order, you really can think of it as the order that you get on the regions when you do this reflecting game. Okay? So let's talk about this a little bit more carefully. For example, let's think about this. Let's think about the fact that when I say U is less than V in the weak order, that's equivalent to saying that the reflections that shorten U are contained among the reflections that shorten V. Okay? So let's draw this picture again. But instead of labeling by the elements of the group, let's label by the sets TL. Okay? So for each one of these guys, I'm going to tell you which reflections make it shorter. Okay? For example, which reflections make S1 shorter when you multiply on the left? Well, S1 makes it shorter. S2 makes it longer, right? When you multiply by S2 on the left, you go up. And the other reflection is S1, S2, S1. When you multiply S1, S2, S1 by this on the left, I get this. So it makes me longer. So this is the only guy that makes me shorter. And by symmetry, this is the only guy that's going to make this guy shorter. What makes the identity shorter? Well, nothing, right? S1 goes up, S2 goes up, S1, S2, S1 goes up. So nothing makes the identity shorter. What makes S1, S2 shorter? Well, let's see. What can you multiply by on the left to become shorter? You can multiply by S1 and you can become shorter. Right? If you multiply by S2 on the left, you become S2, S1, S2. So that's longer. If you multiply by this reflection, S2, S1, S2 on the left, you get S2, S1, S2, S1, S2, which is S1. So that makes you shorter. So that means that this long reflection makes you shorter. Okay? And by symmetry, here we get this. And for this guy, of course, it's the longest element, so whatever you multiply it by is going to become shorter. So S1, S2, S1, S1, S2. Okay? So this is the element U, and I'm mapping it to the set TL of U. Okay? And of course, if this statement is true, then I should observe that the containments are exactly the ones determined by this diagram, and they are. This is contained in this, is contained in this. This is contained in this, is contained in this. This one is not contained in this one, etc. Okay. Now, what is this saying geometrically? Again, this is S1. This is S2. Now, so I have a natural geometric way of thinking about S1 and S2. How should I think of S1, S2, S1? S1 is reflecting across this mirror. S2 is reflecting across this mirror. What about S1, S2, S1? There's basically a third mirror right there, which is this one. And if you reflect across this mirror, you go from the identity to S1, S2, S1. So you can think of the reflection S1, S2, S1 as a reflection across this mirror. Okay? And by the way, this is why we call these guys reflections. The things that are palindromic, we call them reflections because really you can think of them as reflections geometrically. Okay? Now, what are these sets? Here's the identity. Now here's the set S1. Here's the set S1, comma, S1, S2, S1. And if you look at what this set is saying, it's saying exactly what do you have to cross to get from your home region to the region you're trying to get to. Yeah? You cross S1, then you cross S1 and S1, S2, S1. Then you cross S1, S2, and S1, S2, S1. So here I have a combinatorial set of reflections. Okay. And what it means is geometrically is exactly the walls that are separating me from the region where I am to the home region. Okay. And this is how you can think of these sets.
Does it make sense to go around the long way?
So your question is whether I should consider a walk like this. So no. So let's say that whenever I'm walking from the home region to a region, I want to do it in the smallest number of steps possible, where a step means crossing a wall. So if I walk from here to here, I wouldn't want to go around because I would cross more walls than is necessary. Okay? But that's a good point. Because, for example, what are the different ways of getting from the home region to this region in the shortest possible way? There's exactly two ways, which is going this way or going this way. And you see exactly the shortest walks from a region to another region are exactly the reduced decompositions. Yeah? So now we can think of a reduced word, which was this kind of combinatorial thing that you may or may not be happy with. Well, you may prefer to think of a reduced decomposition as walking in this picture. Yeah? S1, S2, S1, S2, S1, S2. So all of a sudden, this picture really makes a lot of the things that we have said combinatorially, we can think about them geometrically. And so let me give you a dictionary from geometry to algebra and combinatorics, which is basically the dictionary for how to go back and forth from this picture, which is geometric, to this picture, which is combinatorial. So here's geometry, and here is combinatorics. Combinatorics and algebra. Okay. So maybe what I'll do is I'll just write things here, and you're going to tell me how I should translate them. Okay. So for example, when I talk about the regions, in this geometric picture, what do I mean algebraically? What are the regions algebraically? They're just group elements, right? So regions are group elements. This is my set W. Okay. So I'm going to write a bunch of things here, and I'll leave you some time to think about them. So what are the walls of the home region? What are those called in this language? Or I'll let you think about it. Let me write the whole left column, and then we'll discuss what the right column is. So what do the walls of the home region mean? What do the reflecting hyperplanes mean? Well, let me just say hyperplanes. So I'll give you some entries of the left column and some entries of the right column, and then we'll translate. So reflections that shorten an element, the set TL of W, weak order, and reduced words for W. So let's go down this list. What are the walls of the home region? They're precisely the generators, S. Which are also called the simple reflections, right? What are the hyperplanes? What do I mean by hyperplane, first of all? Remember, a hyperplane is just any of these walls that you see here. So what are the hyperplanes combinatorially? They're just the reflections, right? Okay. Reflections that shorten an element. So first of all, an element corresponds to a region, and the reflections that shorten this element are precisely the hyperplane separating your region from the home region. Exactly what you said. Hyperplanes separating a region from its from the home region. Okay. So weak order. What's the weak order geometrically? It's basically the order that you see here. The poset of regions ordered by basically how far you are from the home region. Where by far I mean exactly this, right? I mean that a region is farther than another region if the hyperplanes separating this region from home are fewer than are contained among the hyperplanes separating this region from home. So this is the poset of regions by distance from home, let's say. Let me not say by distance because distance is a number. Let's say by separation from home. Okay. U is less than V if the hyperplanes separating U from home are contained among the hyperplanes separating V from home. And reduced words for W. Well, they're basically the shortest paths from the home region to your region. From home to your region. So this is a very powerful dictionary that we will be using very much. Now, I'm doing it in this concrete example where we have this real geometric representation of S3. And so what I'll spend the next few classes on is that I want to show you that this claim that I have made, and I want to make it more precise, that any Coxeter group you can think of as a geometric thing, that basically looks like this. Maybe not quite like this, but more or less like this. So we'll make that precise over the next few weeks. Okay. Yeah, because
if you look at S4, it's just so complicated.
for example, what does S4 look like?
Should that be in 3 dimensions, or are we going up beyond that?
S3 is in 2 dimensions, so S4 is in 3 dimensions.